Okay, listen up. So the first part of class today, we're going to kind of review everything that you have for this quiz. Some of you today, the rest of you Friday. The first part of the quiz is the input and output of sine and the coordinates. It's input and output of sine and cosine and their coordinates. So when you look at this, where do you see the input? Where in this, what are you looking at to see the input? Theta. Okay? It's the input into sine. Okay? And what are you looking at to think about what the output is? What up there represents the output? Okay, yeah, so it could be the whole left side. What about on the right-hand side? What would you look at the right-hand side that represents the output? The whole thing, right? Okay, so while you're putting your heading on and turning in your homework, this is not to put in your homework like last time. This is in your notes for practice. I want you to write out, see if you can do it without looking at your notes from before, the specific and thorough meanings of this input and this output of sine. So practice. So you're turning your homework in. Once you get that turned in, then what are the inputs and outputs of sine specifically? Okay, so we're still turning it in. How about you, Hira? What's the input into sine? Yep, what is theta? What angle is theta? Yeah, which one? Which one? Angle measure isn't going to cut it. So we need to be very specific about which angle it is. Let's try Diana. What angle is theta? Okay, that's honest. We were working on this. Omar, where's Omar? Not here. Oh, you are here. Omar, tell me, what angle is theta? Okay, yeah, so like the last 2 or 3 classes, really been trying to stress the importance. To understand what sine is, you've got to know exactly, specifically, what the input is and what the output is. And so I've been hammering this mantra over and over again. So at some point, we've got to learn it. We've got to memorize it. Scott?
Angle swept counterclockwise from the 3 o'clock position on Circ.
Right. The angle swept counterclockwise from the 3 o'clock position. Usually, most often we've been using radians, but it could be other angle measures as well. Okay? If you haven't memorized this, right now, it's 2 points on your quiz. 2 points on your quiz, memorize this. Okay, output of sine. Frank, what's the output of sine? What does the sine give, or what is the sine? Okay, in? What's the units of that? Okay, he said the horizontal distance, the vertical distance from the horizontal diameter and radius length. There's one little thing we got to improve on there. So it's not just from, above, right? Because we're going to specify what's positive above, and then below would be negative. Okay, so the vertical distance above the horizontal diameter of the circle and radius length. And Frank, what coordinate is that? Vertical distance is which coordinate? No, which coordinate? That's the y coordinate. That's the y coordinate on the circle. Okay? And I should say on the unit circle, right? It's the y coordinate on the unit circle. Okay, so this is 5 points of your quiz. Okay, so now without looking at your notes, see if you can do cosine. Input into cosine, output of cosine. 30 seconds, go. Is Elizabeth here? Elizabeth over here. Elizabeth? No? Zach Wilden, tell me. Input into cosine. Right, and what is it? Right, angles, what same angles before. It's the same input as sine. The angle swap counterclockwise from the 3 o'clock position on a circle. Okay? Michaela, it's the output of cosine. In? And what's the unit for that? What do we measure that in? Okay, so radians is openness. So what's the distance equivalent of radians? Radius lengths, right. So the horizontal distance to the right of the vertical diameter of the circle in radius lengths, and what coordinate is that? You said the y. Agree with that? Well, if you're not sure and you know the definition, you got it. What's the horizontal distance on a graph? X or y? X. It's the x coordinate. Okay, so if we're going to understand and use and apply cosine and sine, the first thing we have to do is we're going to memorize these, okay? And then not just memorize them, then they make sense to us, right? We have this image of a circle and what quantities are happening here, and then we want to apply and use them in situations, okay? But that's the goal, that we can understand and apply cosine and sine, but we can't do it if we don't, first of all, know these meanings, okay? These meanings, and so that's why I'm emphasizing it so much, okay? So that's the first part of your quiz, 10 points. The remaining 66 points is what I'm about to show you, which we did on Friday, but I'm going to go through it fast again, is filling in all the blanks on this. 66 points, okay? So notice, not only are there the radian measures, but you also have to know all the degree measures as well, okay? When you put the radian measures in, to keep this as clean as possible, use that. Here are the radian measures, right here on just inside the circle. Use those as the fraction bar, okay? Don't make the fractions above that. Use that line as the fraction bar. It'll just make a cleaner result, okay? But so there's 66 blanks to fill in here. And you've got the 10, so that makes the total possible points on the quiz 76 points, okay? The quiz is out of 20. Okay, so 100% of the quiz is 20, so this is how it works. Once you get 56 points, then you start earning points on the quiz. So from 56 to 76, correct, is your score from 0 to 20, okay? So as soon as you miss any 20 blanks or more, you got a 0 on the quiz. Okay, so we got to learn. So this should be easy. It's just a matter of knowing what you're doing. Okay, and filling it in. Doesn't make sense. So once you get your first 56 correct, now you're earning your score after that from 0 to 20. And all right, so let's talk about this. So it all started with taking the radius length and putting it on the circle, and that gave us an angle. What angle did that give us? 1 radian. And from 1 radian, we just keep laying radius lengths on the circle, so we get 1, 2, 3, 4, 5, 6. And that's all good, but it doesn't, we said we wanted some nice symmetric places on the circle, right? So that was based on halfway around. So if it was 3 radians, didn't quite make it halfway around, what number of radius lengths made it exactly halfway around? Pi. 3.14159, and so on, right? So pi gives us exactly halfway around, and based on pi, we can get symmetric angles, right? So we can start by looking at pi broken up into angle of 1/4 of pi. And so to get the angles that are 1/4 of pi, all you have to do is start here in the first quadrant, which would be 1 pi over 4, and just count. Just count around the circle. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay? You just count pi over 4s. 1, 2, 3, 4, 5, 6, 7, 8, and that gives us 4 new angles. These 4 are our new angles. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And then we did the same thing again. We took pi and we said, let's make it into 6 equal angles in the top half of the circle. So the blue ones are taking pi and dividing into 6 equal sweeps of angle. And so again, you just count. Just count 1, 2, 3, 4, 5, etc. So here, let's do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so the reason I'm telling you this is a nice way to be able to create like your quiz without having to memorize anything. If you just know how to count, and you know that you're counting pi over 4s, and you're counting pi over 6s, then you have all the radian measures. Now some of these simplify, right? So which ones don't simplify? These 4 don't simplify. They're true, so they're going to stay with a 6 in the denominator. Pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. They'll stay. Okay, but the rest of them all simplify. And so the other new angles that we get are these. And these all simplify in 2/3. So they become pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So those come from the 6ths, but then they simplify into 2/3. So these 4 angles, these new 4 angles, are over 3. And then finally, we've got the 4 easiest angles, which we knew what those were already. So we'll switch those back to pi over 2, pi, 3 pi over 2, and 2 pi. So these are what we call the 16 key angles. But sometimes students get so focused on these 16, and they see an angle like in a situation, and they say, oh, that angle is 5 pi over 6, or that angle is pi over 4, when it's not necessarily. These are just the nice 16 symmetric angles based on pi over 4 and based on pi over 6. So how many angles are there between 0 and pi over 2? Are there 3 angles? There's an infinite number of angles. It doesn't make the rest of the angles less important. It's just that these are symmetric based on pi over 4 and pi over 6. So, again, around the circle there's an infinite number of angles. None are more important than others. Okay? And if you came to an existing situation, you wanted to measure an angle, the chances that it's one of these 16 are like slim to none. Chances are it's some other angle in between these. Okay? So keep that in mind. Don't get so focused on these that like any situation you see, you only see it in the light of these 16 angles. Okay. So let's see here. Then from there, we wanted to get the sines and cosines of these. The sines and cosines. So we looked up in the first quadrant, and we first worked on, so we got all these, you can watch it again, but the cosine and sine of pi over 6 is radical 3 over 2 and 1/2. And that is basically approximately, right? So the cosine is approximately 0.86, right? It's this x coordinate or this horizontal distance to the right of the vertical diameter, 0.866. In exact form, it's radical 3 over 2. The sine, or the vertical distance above the horizontal diameter, it's the y coordinate, is exactly 1/2. Okay? And then for pi over 4, because we're halfway up, the sine and cosine are the same. We're sweeping halfway to pi over 2. We end up with symmetry here. Both of those are about 0.7. Exactly, they're square root of 2 over 2. And then finally, this is symmetric with pi over 6. So this time the x-coordinate, or the cosine, is exactly 1/2, right there. Horizontal distance is 1/2. Vertical distance is 0.866. Okay, so if you know those three, and of course you should know the top, bottom, left, and right side of the circle, that should be easy. But if you know these three, then you know the sine and cosine of every single key angle just by applying the right positive or negative to it. So in which quadrants is the cosine positive? In which quadrants? And remember, this is our 1 is here, 1, 2, 3, 4. In which quadrants is the cosine positive? 1 and 4. Horizontal distance to the right. Okay, in which quadrants is the sine positive? 1 and 2, where the vertical distance above is positive, or where we're above, right? Okay, so based on knowing that, using these values and the symmetry of all the angles, applying the right positive and negative, you know the sine and cosine of all these. So practice.
So on the test, you want it like that on decimal points.
Exact form, right?
Do you have any tricks to memorize that?
What's that? Which? Well, I gave you the tricks for angle. You're talking about the sines and cosines? All you got to know is these three values. Radical 3 over 2, which is the greatest one, right? That's like the 0.866 number. 1/2 is the least. And radical, so you just need to know three values and get these three right. And then, like I said, the rest are all just based on symmetry, putting the right pluses and minuses on them. And that's what we're going to practice right now. So practice these with the person next to you. Answer these questions. Go. Okay. Let's see how we did. Cosine of 5 pi over 6. Yoslin. Where's Yoslin? Cosine 5 pi over 6. What do you think? Positive 1/2. She wants cosine is positive 1/2 there. Angelica, what do you think? Yeah, Angelica. Right, so you actually did the sine, Yoslin. You did the sine. the sine of that angle is the vertical distance is 1/2. But cosine is the horizontal distance to the right, and so that would be the same as pi over 6, but we're left, so it's negative radical 3 over 2. All right, sine of 2 pi over 3. Daniela. The sine of 2 pi over 3. Okay, negative square root of 3 over 2. Positive, right? So that's the vertical distance. It's going to be the same as that right there. 0.866 or radical 3 over 2. Cosine of 7 pi over 4. Jonathan. Cosine. Square root of 3 over 2. Seven pi over 4 is going to have the same numbers as positive or negative. Cosine's positive because we're to the right. We're to the right. Okay. Sine of pi. Malenko. 0. It's the vertical distance above horizontal diameter at pi. Would be 0. Okay. Cosine of 7 pi over 6. Let's do cosine of 4 pi over 3 instead. What's the cosine of 4 pi over 3? Where is Moises? Negative a half, right? So it's going to be the same as the cosine of pi over 3. We just got to put the right positive or negative on it. Since we're left over here, it's negative 1/2. Negative 1/2. Okay, what angle gives a sine of 1/2? What angle gives a sine of 1/2? Anthony. What's that? 60. Are you talking, so 60 degrees? So that's here. Does this give a sine of 1/2 right here? That's 60 degrees. Is that what you meant? That. So you mean here? So he said pi over 6. Pi over 6 gives a sine of 1/2. Agree? Okay, also 5 pi over 6. Do both those angles give the same vertical height? Yeah, so we're coming up here. On the way up, we're going to hit that height of 1/2. And then as the angle increases on the way back down, we reach the angle of 5 pi over 6. We're going to hit that same height of 1/2. Okay, so is the sine a function? Is the sine a function? Yes or no? What do you think? Do you agree? Someone said no. Agree with that? It's not a function, or you don't agree? Is sine a function? Oh, some of you are saying yes. Why is it a function if these two angles both give the same output? So remember about a month and a half ago we talked about what is the criteria for a function. What makes it a function? Every input has exactly one output. The fact that two different angles have the same output, does that violate that condition? No, it doesn't violate it. If I put the angle pi over 6 in, do I get exactly one output? Yeah, I get 1/2. And if I put the angle 5 pi over 6 in, do I get exactly one output? Yep, they're the same, but that's okay. What's the problem? If I were to put an angle in and somehow got two different vertical distances, then we'd have a problem. But is that going to happen? No, you put an angle in, you're going to end up at a certain point on the circle. There will only be one vertical distance corresponding to that final location. So sine is definitely a function. You get one vertical distance for every angle that you input into sine. Now those output values repeat. They repeat over and over again as we go around the circle. But that does not violate the condition of a function. Okay, what angle gives a cosine of radical 3 over 2? What angle gives a cosine of radical 3 over 2? Yeah?
Pi over 6 and 11 pi over 6.
He wants pi over 6 and 11 pi over 6. Agree? That's right. Are there any more angles that give a cosine of radical 3 over 2? What's that? That's negative.
Cosine is negative.
Cosine of negative pi over 6. And cosine of negative 11 pi over 6. So we got 4 angles. Any more?
No, the questions that's negative.
Oh, my fault. All right, let's start over. What angle gives a cosine of negative radical 3 over 2? Over here, this is our horizontal distance. That's negative radical 3 over 2. So we got this angle here, 5 pi over 6, and then 7 pi over 6. Are there any other angles that give that cosine? What's that? 8, and why? He said there's an infinite number of angles.
Because you can keep going around the circle again and again and then just end on that point.
Yeah, so we've been focusing on all the angles from 0 to 2 pi, but we can have larger angles than 2 pi, meaning start a new rotation. We can go to 3 pi. And 3 pi would be like a circle and a half of rotation. So as long as we keep increasing the angle, we can get as many angles as we want that will give us this cosine of negative radical 3 over 2. Every time we hit that point of the circle and this point of the circle, we have an angle that gives us that cosine, and you can as many as you want, an infinite number, by continuing to increase the angle, or you can go negative, right? So you can go clockwise around the circle, which would be negative angles. Okay, any questions on your quiz or all this stuff? Okay, so again, 66 points for filling in the blanks here, 10 points for the sine and cosine, and you got to get 56 right, then to start earning points out of 20. So the first 56 that you get right earn you the ability now to get a score out of 20. All right, so look at investigation 5. I think it's page 170 something. 75? $275. There we go. 270. 275. Investigation 5. Okay, so this is about twirling a ball in a string, and it says that the string is 2.3 feet long. And every second, the ball sweeps 2 radians. Every second, the ball sweeps 2 radians. Okay, so let's write down the info here. So the radius is 2.3 feet, and it rotates 2 radians per second. So now we're bringing time into the situation. So far we've only had angle and then radius lengths, either vertical or horizontal radius lengths. Now we're bringing time into it. Okay, so let's start by saying, so how could we write theta in terms of t? How could we write theta in terms of t? So as time goes by, the amount of time that goes by determines how much angle has been swept. So the question is, according to what? According to what relationship gives us how much angle has swept? So if you're not sure in a situation like this, here's what I recommend. Make a table. So take some values of t and write down some corresponding angles. So at time 0, what angle has been swept out? And at time 1, after 1 second, how many radians do we have? 2. Is it 2 or 2.3? No, we have dissension in the ranks. So the radius is 2.3, and it's rotating 2 radians every second. So how many radians will it go in 1 second? 2. It has nothing to do with the radius. So in 5 seconds, how many radians does it turn? And in 100 seconds. All right, so then in t seconds, how many radians? 2t. So this is our relationship to t. All right, let's put that on hold for a second. Let's look. I've got this graph here. This graph is showing some distance in radius lengths as a function of theta. So we'll put theta here. So what is the angle theta right here? Well, let's start over here. So here's 0. So this is showing some distance in radius lengths as theta increases, okay? So this is showing that we are at 1 radius length when angle is 0, and then that distance decreases to 0. So which quantity is that this graph is showing? Is it showing vertical distance or horizontal distance? Horizontal distance, good. Because at 0, the horizontal distance is 1. And then okay. What's that? No, what angle is our input into cosine or sine? What angle? Angle swept counterclockwise from 3 o'clock position. Always 3 o'clock position. So that 0 angle there is always going to be the 3 o'clock position. So then we're saying what distance is 1 here? Horizontal or vertical position? Horizontal distance is 1. And as that angle increases to pi over 2, what does that horizontal distance do? Goes to 0. So this angle right here is pi over 2. And then what happens to that horizontal position here to here? It goes from what to what? Horizontal position from 0 to negative 1. So that's this part of the graph here, 0 to negative 1. So this angle is? That's our pi. Next part of the circle. Horizontal position goes from? Negative 1 to 0. That's showing here. Negative 1 to 0. Angle. 3 pi over 2. And then finally, last quadrant. Horizontal position goes from? 0 to 1. And then what would happen if we let the angle keep increasing? Like another rotation or another several rotations. The graph would repeat, right? Because it's the same horizontal distances repeated all again every time you go around the circle. So this thing would just keep repeating. So what this is called is this 2 pi here then. 2 pi is the interval of input that results in one full, what we call cycle of output values. one full cycle of output values. And there's a name for that. The interval of input. So this is about the input that results in the output going through one cycle right until the point where it's going to start over and do it again. So that interval of input is called what? This is the period. The period of this is 2 pi. So the period is 2 pi. The interval of input that results in one full cycle. So what function, it's called f, are we graphing here? So the input's the angle, swept counterclockwise from 3 o'clock. The output is the horizontal distance from vertical diameter and radius lengths. So what is that? Cosine of theta. So that graph that's shown there is cosine of theta. The period of cosine is 2 pi because that's how much input has to go by to get a full, exactly one full cycle of the output. Or it's going to hit all those output values until the point where it repeats it again. Okay, so if f equals cosine theta, how can we write a function g of t? So how can we write a function g of t that will give us the same output, the horizontal distance and radius lengths, horizontal distance to the right and radius lengths, but now the input is t? How can we do it? Cosine of? Yeah, we found what theta was in terms of t, so we can put 2t. So the cosine always receives an angle. So if you want to write a function of time, then you just need to know what that expression of time is that gives you the angle. And you could put it there because cosine always wants an angle. It always wants the angle swept counterclockwise from the 3 o'clock position. And so that's 2t. So now the period of this function is different because now we're saying what interval of t, because t is our input. So now we're asking what interval of t gives us one full cycle of output values. Okay, well the way that we do that is we know what the period of cosine is. So this expression 2t needs to, since it's the angle, since it's theta, we need to make it equal to what we know the period is for theta, or for cosine, and then find the equivalent, or find the value of t that's going to make that expression, theta, equal to 2 pi. So this is what we set up to figure out what the period is of g, our g function, which is now in terms of time instead of angle. So the period, so again, what are we saying here? We're saying we want the time such that 2t, or the angle, is 2 pi. Because we know that's what's going to cause cosine to do one full cycle, is when that thing right there is equal to 2 pi. So then Tp is? You just divide by 2 and you get pi. Okay, so now if we were rewriting our scale in terms of time, what time gives us one full cycle? So what time should I put right here? Can you turn the radio off? I can hear that. And so certainly people around you can hear it a lot better than me. Okay, so what time gives one full cycle? Our period, right? Pi. And so then this would be halfway around, half a cycle, pi over 2, or half a period, pi over 4, and 3 pi over 4. So for the f function, it would be the black scale there. Pi over 2, pi, 3 pi over 2, 2 pi, that's our period. But for g, it'd be the same outputs, but now we have a different period. the period of g is actually the amount of time it takes for this ball to go around, which is pi seconds. In pi seconds, it makes it all the way around. Okay, any questions? Does that make sense? All right, so that's a little slow. So it would be very difficult to actually swing a ball and so that it swings at 2 radians per second. That's really slow. So something more realistic would be like 9.7. I'm just making that up. 9.7 radians per second. Or what is that? Every second? 6.28 radians is 1, so this is about a rotation and a half every second, okay? So if we want to write h of t, it would be cosine. So again, this whole thing is still the angle in radians, but we need what that angle is in terms of t. So what is our, after 1 second, how many radians does this ball go? 9.7. Every second it goes 9.7 radians. So after 100, (970) radians in 100 seconds. So after t, 9.7t. So that's the angle. 9.7t is the same as the number of radians, and that's what cosine accepts. Number of radians swept counterclockwise from 3 o'clock. So then the period, we need 9.7t to reach what value to get 1 full cycle? Yeah, so we need that, the angle going into cosine, once it reaches 2 pi, the corresponding t that makes that angle 2 pi will be the period. 2 pi over 9.7, which I think is, if I remember, about 0.65. So what does that number mean? 0.65 seconds. What does it mean in the context of this situation? 0.65 seconds. Nice. Right, 1 revolution of the ball, or 1 period, is 0.65 seconds, about 2/3 of a second. Okay, questions on that? So I want to kind of summarize one last thing here. Any questions on, so what is the period? So for any given function, the period, you got to look at your input. It's the interval of input that results in 1 full cycle. And the way that we can figure that out is knowing that it always starts from knowing that the period of just the cosine is 2 pi. So whatever you're putting into cosine, you just make that equivalent to 2 pi, and then solve for your input variable. That's going to be the value that makes the angle 2 pi and gives you 1 full cycle. Yeah?
Is 9.7 something for another question?
I just made it up. Yep. Okay, so can I erase what's up there? Okay, so just take me a second here to get caught up. Okay, so here's cosine theta. So now we're saying cosine of 2t. So theta is no longer the input into this function. What's the input into this function? Time. Time is the input. But cosine still always takes an angle. So we need a name. Now that we have an expression for the angle, we need a name for that. And what we name that is, we name that the argument. So what we were calling before the input into cosine, like for your quiz, now as an expression, we call that the argument. What quantity is the argument? What quantity is the argument? What kind of quantity is that? Is it time? Is it time elapsed? The argument is time elapsed. Agree with that? No. No, what is the argument? It's the angle. It's the angle swept It's still, the argument is the totality of what we're putting into cosine. So it must be the angle swept counterclockwise from the 3 o'clock position. Okay? The input into the function is time. But the argument, what we're putting into cosine, is always angle swept counterclockwise from 3 o'clock. Don't write angle on your quiz. Swept counterclockwise from 3 o'clock.